One Wednesday morning, developer gets up, they get ready, and they finally sit down at their desk, flip open their laptop, start flipping through the usual dashboard. They see a latency graph and they're like, is that a little increase? Could that possibly be related to the feature I deployed yesterday? Maybe I can find out from logs. So they go over to their log aggregator and they type in a query and hit run. Might as well go get another cup of coffee. That's it, that's the story. Someone talks to them, it's gone. Let's talk about using serverless functions for real-time observability. I'm Jessica Kerr. I'm a developer advocate at Honeycomb after 20 years in software development, so I'm a developer background.
And I'm Fong-Jones, and I'm a developer advocate, and I work on improving SRE outcomes. So today we're going to talk about three things. First of all, how we found serverless useful for on-demand compute. Secondly, how we've encountered some of the sharp edges with using serverless for on-demand compute. And finally, we'll give you some practical tips on how to take these lessons home and apply it to your own environments.
Right, so first, AWS Lambda, that's exciting, right? Let's use it. Okay, but what are we gonna use it for? At Honeycomb, we want to optimize our custom data store retriever. Custom data store, whenever you hear that phrase, you've gotta say, why? Well, our custom data store is a distributed column store for real-time event aggregation. Why? We use the real-time event aggregation for interactive queries over traces. What's that for? Well, observability. There's a word I've heard 100 times already at this conference. Back in 2015, when our co-founder, Charity Majors, brought the word observability to software conferences, it didn't mean anything to people because that word wasn't yet used in software. Now, when I use the word observability at this conference, it doesn't mean anything because everyone uses it in software. Well, to distinguish observability from monitoring, in monitoring, you're like, okay, we know we need to watch out for some things. So I'm going to decide what we need to count, and we're gonna count all the things, and then we're going to store all those counters from second to second so that when we need to graph them, whoosh, it's really fast. In observability, we ask, well, what do you want to see right now? And we store all of that in raw event data so that we can make every graph fast. But making every graph fast without pre-aggregation is a challenge. And that's why we have a custom data store. But this is what that experience is like. This is what we're going for. So say I want to ask, like, okay, how long do our Lambdas run on AWS? How long does each one take? Okay, so I'm going to need to find those spans. I know the service name is Lambda. All right, we've got some of those. I can count them. Well, name. If I just group by name, I can probably pick out the one I want. So there's a lot of names, but that's fine. Well, we can see all of them. Aha, invoke. That's the one I want. I can filter by just those. Let's see just the invoke spans this time. All right, there they are. Okay, let's get the median duration. And all that aggregation is happening at query time while I wait. So the goal here is that we have interactive investigation of production behavior. You can see the events that happened a second or two ago in production, and you can aggregate those, find the next question you want to ask, and ask that, and iterate. It's important that this is interactive. If you have to take a sip of your coffee while you're waiting for a dynamic aggregation over millions of events, I'm okay with that. Maybe 2 sips if it's like a really group by 4 fields and aggregate 3. But if you have to get up and get a new cup of coffee, if you have that urge, we have failed because you will get distracted, especially if you're a developer, you'll go think about something else.
Squirrel.
Exactly. exactly. Retriever loves squirrels too. So our data store retriever, how does this work? Events come in from your application, and we store them. And then queries come in from the Honeycomb UI, and we do all those aggregations and produce the queries. So how do we make this fast? One thing is we're distributed. So the events come in, and we split them up into partitions of a Kafka topic, and each customer and data set has multiple partitions, and we just round robin between them because we don't know what you're going to query for. Each retriever node, they're actually duplicated. I just show one here, but they are redundant. Each retriever node writes those events to its local disk, and then when a query comes in, it can come into any of the retrievers, and that retriever will fan it out to all the other nodes that have relevant data. They'll all access their disk. They'll add up and aggregate what they have, pass it back to the original retriever that received the query, and that one will finish the aggregation and pass it on. So we've got a parallel map reduce process going on here. So the distributed part both makes it scale better and makes it faster. Another trick we use is that retriever is a column store. And this is important because we want you to be able to add all kinds of attributes to your events. We don't care how many, and that's not going to slow down your query because it's not going to slow down our reads, because we're only going to look at the files that contain the column that you filtered by, aggregated on, or grouped by. And then, of course, we have to divide these files up somehow. So we segment by timestamp, and technically, Honeycomb does index on one thing, and that's timestamp, because all of our queries have a timestamp associated with them. That's one of the properties of this use case. All right, so we've got all these segments with known timestamp ranges. They overlap because arrival and timestamp are not the same, but we know where they are, and whenever we fill up the allocated disk space, then we can delete the oldest segment and start a new segment. When a query comes in, we know which segments it needs to read. So we're reading only the segments where your time range overlaps and only the columns that you asked for. This makes it fast. Until we have everyone's favorite problem, more customers and bigger customers. And so much data is coming in that these local disks on our EC2 nodes start to feel really small. And those segments of data that we were deleting from like last week, suddenly that segment we're deleting because the disk is full was from 15 minutes ago. That's not okay. That's not enough data. In fact, last week isn't enough data. We want 60 days. 60 days, that's a lot of data. And what do you do when you have way more data than you can conceive of holding? You put it in S3, of course, where all data eventually goes. Okay, so now, instead of deleting that oldest segment, we're just going to promote it up to S3. Each retriever node is still responsible for the segments that it put in S3. And when a query comes in, retriever will read what it has on local disk and also whatever it needs off of S3. And that's fine. That's cool. Now people can run queries for over 60 days of data. Oh no, people are running queries over 60 days of data. That's not fast. Suddenly our response time is growing linearly, at least it's linear, but it's linear with those segments queried because there's just a lot of work to do. And we had to change our maximum query timeout from a few minutes to an hour. I mean, that's beyond a cup of coffee. This is roast the beans and grind them and make a new pot. Good for your coffee, bad for your observability. So this was not okay. Retrievers are like, please can I just have more compute? I really need more compute. But only sometimes. Not like all day, only when they feel like playing. Only when someone runs a query with a wide time range over a large data set, then we need a lot of compute for like 10 seconds, because that's how long we want the biggest queries to take. So we need it very quickly so that we can return within a few seconds, and we need it for a very short time. So it doesn't make sense to spin up more EC2 nodes. That's really expensive to carry all that compute all the time for these peak loads. this is too much for one retriever. As I want to mention that the bottleneck here is not reads. We can actually read it faster than we can do all of this sorting and filtering and aggregating. Because we're doing all this compute on the fly at query time, compute is our limitation, our first bottleneck anyway. So okay, when it's too much for one retriever, we give it some helpers. So our retriever was written in Go anyway. We break up this little bit, we give the retriever a helper, and we run it in AWS Lambda. And so for whenever a retriever needs to read data off S3, it doesn't do it itself. It reads its local disk, and then it spins up a Lambda for every 8 segments or something. And the Lambda reads the data from S3, does the compute to do the aggregations, ships it back to its retriever. That retriever adds all those up and ships it back to the central retriever that then responds to the UI. Success. Query time is now sublinear. We are able to spend money to preserve your attention when you run a query over 60 days worth of events. And we're able to do this efficiently because we're able to buy that commute in now 1 millisecond units. AWS just increased the granularity of its pricing here. And that's sweet. It's good enough. I mean, Lambda scales up. We can start one in 50 milliseconds, which for a couple seconds query response time is acceptable. And then they return within a couple seconds. And yeah, it's 3 or 4 times as expensive as the same amount of compute on EC2. But when we use it less than 100th of the time that we would have to run an EC2 node, it's a great deal. So everything's good, right, Liz?
Well, there might be some minor adjustments that you need to make, because it turns out that these are ideal numbers. These don't necessarily correspond to what happens in reality. So let's talk about how our use case maybe strains the bounds of what's possible on AWS Lambda. Because AWS did not necessarily design it for this use case. AWS originally designed Lambda with the idea that it's serverless, as in you're serving API requests that are reasonably cheap, and you're just using it as the backend for something that's just a web service, right? That you're not going to spend, surely no one's going to just ask for 1 million requests to suddenly get processed in less than 10 seconds, right? So let's talk about that first lie that Jess may have told you, that Lambda scales. Because it turns out that AWS has a concurrency limit per account, not per Lambda function, per account in Lambda. And that if you try to run more Lambdas than your current AWS concurrency limit is, then AWS is going to return to you a 429, saying, hi, you are currently not provisioned for this. We don't have enough spare Lambdas running, waiting to serve your workload. You're going to have to wait. So you might need to retry. Now, what increases that concurrency limit, you might ask? Well, one of the things that does increase that concurrency limit is running a lot of Lambdas over and over and over again, kind of consistently over the span of minutes. And if you're actually waiting for someone to turn up, like Christina, to run a Honeycomb query, and then they don't turn up, and then AWS is going to say, well, you didn't run a query, so we're not actually going to increase your concurrency limit. So it turns out that maybe you need to actually talk to your AWS account team in order to get them to increase your burst limit, because otherwise, you're actually not going to get provisioned all that extra capacity to be able to run your queries. OK, so that's kind of the first problem, which is that if your workload is spiky and not sustained, AWS Lambda has no idea how to handle it out of the box. So we were able to see this behavior because we were able to see how many concurrently executing Lambdas do we have, and how does this interact pathologically with that requirement to use all of your concurrency for 1 minute before they give you more concurrency. So there are documented limits. The first thing you should do is to make sure that you're retrying requests that return a 429. If you have too many 429s and it's becoming a problem for your workload, talk to your AWS account rep. Or if you're on GCP, talk to your GCP account rep, because it turns out that you should never surprise your cloud provider. We'll talk about some of the surprises we cause the Lambda team, though. OK, next lie. 50 millisecond median startup time, right? So if you have a 10-second query, then that should be fine, right? Not every query consistently starts within 50 milliseconds, because functions start up when they do. So this is what the graph of the execution, not of one request in Honeycomb. Instead, this is the graph of the lifetime of one individual Lambda runner. So what you will be able to see if you download the slides later is that there's about 12 milliseconds here spent in the main function initializing. And then we run for a second or two, and then we sleep for a second or two, and then we run for a second or two, and then we sleep for maybe 10 seconds or 20 seconds, right? But it's not necessarily always the case that a cold start will take less than 12 milliseconds. Sometimes it takes 100 milliseconds, sometimes it takes 1,000 milliseconds. And there's another problem, which is that originally, when we had configured this, we had the problem of when you started up, when you were refreshed and asked to run a brand new query, you might not have finished all of the cleanup from your previous query run. Because as soon as you return the request to the client, originally, Lambda freezes your execution, even if you had state that you needed to dump. Like, hi, here's the telemetry from that last request that I ran 30 seconds ago. That's not quite as useful, right? So we had to do some instrumentation to understand what was happening. And it turns out that there's this technology, at least in the AWS ecosystem, called a Lambda layer that allows you to return your result and to keep processing for a little bit so that you have done all of your cleanup and you're ready to actually initialize and do your next request when you're woken up, rather than having to offload all of that telemetry data first. OK, the next thing. 90% of queries return within 1.5 seconds. Anyone want to take a guess as to what that remaining 10%, how bad that can get? The answer is some Lambda functions take as long as 30 seconds to return. Some never come back to us. And it turns out that's not a great thing when you're trying to return results in less than 10 seconds. So the good news here is that this is not Lambda's fault necessarily. This is actually the AWS S3 API's fault. Because remember, all this data lives in S3. So it turns out that Lambda is actually pretty reliable at giving you your compute eventually, like not necessarily within 100 milliseconds, but maybe within 1,000 milliseconds. But then it might block waiting on an S3 API call forever. So what's our answer to this? Well, our answer to this is to use impatience. So if you're one of the last 5 Lambdas or 10 Lambdas remaining in a query that is executing 1 million different Lambdas, well, fine. OK, we'll just retry it. And chances are that the stuck request will become nstuck and will run successfully the next time. So that kind of solves the tail latency problem, that if you just retry the slowest 1% of queries before they complete, then you'll race, and whichever one finishes first, great, you're done. There's another problem, which is that if you have an AWS Lambda function, you can surely feed all kinds of data to it, right? Like you can just feed it the raw payload data from your query engine, right? Not so. It turns out that AWS Lambda expects your functions to accept JSON. That if you don't feed it JSON, it's going to just reject the request with some kind of arbitrary problem. So it turns out that we have to generate that listing of S3 files. And if it gets too big, we may even have to generate the listing of S3 files, upload a file containing the list of files that you need to examine to S3, and just give you a JSON lob that says, go check here for your query arguments. Same thing with the return value. A Lambda function can return up to 6 megabytes. If your results are bigger than 6 megabytes, for instance, if you're grouping by something super high cardinality, and you have one return value for every group, that might get a little big. So again, you have to go and use S3 or something else to pass larger payloads around. OK, finally, let's talk about cost. So yes, AWS Lambda per core second is about 3 to 4 times as expensive as EC2. And this is pretty good, because if we were running EC2 flat out, we would get only about 1 or 2% utilization out of those EC2 instances. And given the amount of Lambda concurrency that we use, where we use up to, I think, 30,000 concurrent Lambdas at a time now, there's no way that we would be paying for 30,000 AWS instances flat out. That would basically drain our entire company's runway. So we actually do need to keep an eye on it, though, because AWS is notorious about not having great cost controls. you can suddenly blow out your AWS budget if you're not keeping a close eye on it. So we wind up doing queries over our internal Lambda datasets and estimating the cost. And we're able to attribute that cost down to individual customers as well as individual use cases. And it turns out that we have, in fact, blown our cost budgets multiple times. For instance, when we were first implementing service level objectives in Honeycomb, we were repeatedly querying, you like your SLO to look back 30 days. Well, if you query 30 days of data every 1 minute, that's going to add up very quickly if that hits Lambda every single time, even if the result is the exact same thing for the past 28 days. Because it's really only the most recent hour or two that's changing. So we accidentally ran up a $10,000 Lambda bill in 2 days from that, from just us doing internal SLO testing. Whoops. Or sometimes we'll have large clients. For instance, our friends over at Vanguard happen to have a lot of boards. They happen to love the Honeycomb boards feature. Except for if you load the Honeycomb boards feature, it loads a graph for every single board that anyone has ever created at the company. And at a certain point, that adds up, right? So basically, Lambda costs can really surprise you, and there's nothing to stop you, right? Like, it's not like 8 EC2 instances where you can kind of easily see how many EC2 instances am I running. If you issue it at Lambda Invoke, AWS will happily do it for you and charge you for it. So how do we make it less? Because right now, AWS Lambda actually is the #1 cost driver at Honeycomb. Having supplanted the cost of Kafka, having supplanted the cost of the steady state running retrievers, Lambda's the #1 cost driver now. So AWS Lambda, right? Like they said, hey, we have AWS Lambda functions powered by Graviton2. And hey, someone has done testing of Graviton2. I gave a talk at SREcon22 about it. And we found that for EC2 instances, it was great that we were able to get 30%, 40% cost savings. But what happened when I tried to turn it on? Because we were already building for ARM64. Surely this should be super easy, right? And it turns out the latency really sucked. So we had to revert this experiment because it turns out that if we want the results to come back to a developer like Jess within 10 seconds, but some of the queries are taking 20 seconds or 30 seconds because they happen to hit an ARM worker, that's not acceptable, right? Like, there's cost savings, but if you do so much cost savings that you violate the basic constraints of what your service is supposed to do, you've cut costs too far. So the good news, we'd put this behind a feature flag. We were running an A/B test, running 50% on AWS Lambda ARM, 50% in AWS Lambda x86. So I was able to just turn it off, turn it back down to a trickle of 1%, knowing that Lambda impatience inside of our query engine would retry anything that happened to be too slow, whether it was because it was too slow because of hitting S3 and S3 not coming back, or if it was too slow because of ARM64. So I reverted it, and basically within 500 milliseconds, our query latency had gone back to normal. And we were able to have only that 1% trickle go to ARM64. So then I spent months digging into why. I boiled down to 3 factors. #1, remember what I said about don't surprise your cloud provider? It turns out that if you are a very large consumer of AWS Lambda, you really need to be on the same page as your account team because you're probably stretching some dimension of the service. It turns out there is a reason that AWS restricts you to 30,000 concurrent executions unless you talk to them first. In particular, if you go from executing 30,000 concurrent executions against x86 to doing that with their brand new, newly released compute platform, you're in for a bad time. So good news. We talked to our account team, and they said, great, we'll have more capacity for you. And in the meanwhile, you can go up to running 30% of your load on ARM64. So that's what we did. Second problem, our workload, because remember, these Lambda functions are churning through data, and they're churning through data running n-known code paths, right? We don't know in advance which aggregations you're going to try to run in your data. So Go can't inline these functions. Go has to issue a function call because it's executing essentially I hate, by the way, that it's called Lambda in both senses, but we're executing function lambdas, right? Like we're executing variable functions depending upon what the arguments are. And Go really does not like that, because Go, until Go 1.17, was doing all of these calls on the stack, not via registers, but on the stack. And that has a real huge performance penalty if every single function call that you make has to touch memory. L1 cache is fast, but it's not that fast. So with Go 1.17, AMD64 got the optimization to do register calling, but ARM64 did not get it until literally yesterday when Go 1.18 was out. So, oops, OK. So we were able to, because this was the read workload, not the write workload, right, like where we only get one chance to get it right. The read workload means that we're able to experiment knowing that the cost of failure is lower. So we decided it was safe to go ahead and run Go 1.18 pre-release in order to validate that the performance is going to be good enough. And finally, remember when I said that, that it's important to make sure that you're optimizing your files in S3, and that if you're sending a list of files in S3 and you're reading all these files from S3? Jess said earlier that compute was the main limitation. But that's not strictly true. The reason why compute is the main limitation is because we'd already put in the work to make sure that disk I/O was not a limitation by using LZ4 compression, which is basically a really great trade-off of very light on CPU, but still squishes 30%, 40%, 50% off of the consumption of storage, especially when you have these repeated payloads, right? Your user agents are more often than not going to contain a lot of common substrings. So LZ4 is great. We were using it successfully on AMD64 lambdas to fetch the files out of S3, but it turns out that ARM64's library in Go for LZ4 was not optimized. So we had to fix it and give it an assembler optimization. And then we're able to successfully feature flag on 1%, 2%, 5%, all the way up to 30%. So this is what it looks like today. Things look pretty good. We're running 30% of our workload steady state on ARM64 lambdas. And you can see that we're decoupled from the amount of CPU that's consumed on the actual bare metal EC2 hosts. And that most of that workload is instead being performed across tens of thousands of distinct Lambda workers that are successfully executing queries at about the same latency. The ARM64 hosts on Lambda are maybe about 10 to 20% slower, but they're 20 to 30% cheaper, so it works out, and it still is acceptable latency, right? It's OK to go from 100 milliseconds to 120 milliseconds, but it's not OK to go from 100 milliseconds to 1,000 milliseconds or more per Lambda. So what are the takeaways? I think the takeaways for any workload, regardless of whether you're doing an observability workload like we are, but like anything that involves real developers or end users having to wait while you're processing a request, is that serverless can really benefit your use case. So yes, do this at home. So how do you do this? Well, you have to get your state out of local machines onto object storage, because otherwise you're not going to be able to massively parallelize it. After that, you need to make sure that you're able to generate a listing of all of your work units, and to generate a suitable sharding that contains a work list for each individual Lambda to execute. And then you can use serverless functions like Lambda or like Google Cloud Functions to parallelize the object processing on demand and really give you that compute in the instant that you need it. And then finally, you can do that reduction step either with another Lambda if you have a lot of data, or you can just reduce the data. In our experience, it works fine on a single retriever node on EC2. But here's some dragons to be aware of. First of all, don't do this for latency insensitive workloads. Right? It doesn't make sense to spend 3 to 4 times as much if there's no actual human being sitting there waiting for the results. You're better off just letting it run and returning whatever it returns. Secondly, you want to avoid tiny workloads. Right? The reason why we didn't shift all of our processing to AWS Lambda is that if your request is able to return in less than 100 milliseconds, don't pay the cost to talk to Lambda, to wait for the cold start, to wait for the invoke. At a certain point, that introduces more latency and variability than it solves. And then third, right, like there's a statement in like aviation, right, the idea of state your intentions, right? state your intentions to your cloud provider so that they can do the right thing, because they want you to succeed as well. They just need some preparation. All this runs on real physical hardware at the end of the day. And before you actually scale out, make sure that you're tuning things properly. Experiment with the number of items per unit of invoke. Experiment with your CPU and RAM ratios. Make sure that you are actually optimizing your code properly, because it's going to run a lot. And you don't want that bill to balloon to $10,000 per day if it could only be $6,000 or $7,000 per day if you optimized it. Make sure you have adequate observability, and in particular that you're using observability layers to export that telemetry data so that you're not stuck waiting to export at the end of your function call and blocking the end user return or blocking the beginning of the next call. And finally, make sure that you have enough measurement of your cost metrics to know that you're not getting surprised, as well as all the other performance metrics that you would expect to have.
So I see it is a happy story, not perfectly smooth, but still good, like all development. And we're able to scale up our compute, and we will spend money to preserve that priceless resource, developer attention.
So if you're interested in learning more about all of this, this is actually the contents of a chapter in the book on observability engineering, where I've written, alongside with our lead engineer who developed the retriever backend, about how to design things for this kind of real-time observability workload. So feel free to check out a copy of the book, Compliments of Honeycomb and O'Reilly. Oops, sorry, I'll go back so that people can go and photograph the slide.
Good idea. Yeah, just leave it here. Also, find us downstairs. In the next break, I'll be interviewing Charity. Bring your questions.
And that's all that Jess and I have for you today, and we're happy to take your questions, whether you're joining us virtually or whether you're joining us physically in the room.